Welcome, everyone. Thank you for joining us this early evening. My name is Jenny Sabin, professor in architecture and also part of the faculty in design tech, as well as the inaugural chair for our new exciting multi-college Department of Design Tech. And it's really a pleasure to welcome Skylar Tibbits back to Cornell. Skylar participated in an important Preston Thomas Memorial Symposium many years ago now, to launch the Matter Design Computation Program, which is the precursor program to our now installed MS Design Technology program in the Department of Design Tech. So we're super excited to have you back, Skylar. We share lots of synergies, and we're really thrilled to hear about your new work. And with that, I'm going to ask Laura Gonzalez to introduce Skylar. Laura is a visiting lecturer this year in our department, teaching studio. And with that, I'll pass it to you.
So hi, everyone. As Jenny mentioned, my name is Laura Maria Gonzalez. I'm a visiting lecturer in the Department of Design Technology, and today I have the pleasure of introducing Skylar Tibbits. So before my time at Cornell, I attended MIT, where I first met Skylar. I had the amazing privilege of having him as my advisor and mentor, and I was fortunate to teach alongside him in the course, How to Design Almost Anything. What became clear to me about Skylar during that time is that he's not afraid of the unknown. He's not afraid of uncertainty, of risk, of pushing the boundaries of design into uncharted territory. There are no assumptions. From the fundamental behavior of materials to the capabilities of fabrication tools, every aspect is examined, challenged, and transformed into an opportunity for discovery. You certainly have to think this way and be this bold to be where he is today. Skylar is an associate professor of design research in the Department of Architecture at MIT and the co-director and founder of the self-assembly lab housed at the MIT Morningside Academy for Design. Skylar's work focuses on programmable matter. He envisions a future where it's not just artificial intelligence shaping the world, but material intelligence, where matter itself is programmable. His projects span across scales, from thinking about matter at the nanoscale through projects such as DNA printing, to large-scale interventions like growing islands, which explore climate-responsive infrastructure. He thinks across fabrication methods, from 4D printing to rapid liquid printing to metal. And he thinks across industries, from active textile tailoring to innovative construction techniques like slip-form rock jamming. His daring and provocative approaches have been widely recognized. He has received numerous awards, including the R&D Magazine Innovator of the Year, National Geographic Emerging Explorer, Wired Fellow, Gifted Citizen, Fast Company Innovation by Design Award, the Architectural League Prize, the Next Idea Awards at Ars Electronica, the Visionary Innovation Award at the Manufacturing Leadership Summit, and he was named TED Senior Fellow, to name a few. He's also shared his thinking through several influential books, including Things Fall Together, published by Princeton University Press, Self-Assembly Lab, which came out with Routledge, Active Matter from MIT Press, and Being Material, always also from MIT Press. In addition, he's the editor-in-chief of the journal 3D Printing and Additive Manufacturing, and has been widely published in outlets such as the New York Times, Wired, Nature, Fast Company, and in various peer-reviewed journals and books. On a personal note, one of the most memorable pieces of advice that Skylar ever gave me was simply to dream bigger. It's actually a piece of advice I share with my students today. It sounds super cliche, but I remember meeting with him to go over my thesis progress and being completely wrapped up in the technical difficulties of a singular experiment. But Skylar was thinking about this on a completely different scale. He wasn't just focused on the problem in front of me. He was lifting it up to the level of radical possibility, of science fiction made real. He could step back from the mechanics of a study and remind me of the larger implications of how rethinking materials and systems could fundamentally shift the way that we think about matter, life, and design itself. Through his work, Skylar challenges us not just to solve problems, but to dream bigger about the role design can have in shaping the material world of the future. And with that, please join me in welcoming Skylar Tibbits.
Thank you so much. Thank you for the invitation and the introduction. I don't remember saying any of those things, but I'm glad they were memorable, hopefully useful. Um, and Jenny, I think it was exactly the same room, same location. I don't know how many years ago. So wonderful. Yeah, 2016. Whoa, that's wild. Um, and there are so many parallels that we can talk about afterwards as well. But I'll give you a bit of a background of the things that I'm doing, and then I'll get into the research. But I run this journal, the 3D Printing Additive Manufacturing Journal. I'm passionate about this because it brings together all different disciplines from design and architecture to material science and biology and computing. And I added the plus sign. And that when I stepped in, because I wanted to go beyond 3D printing, I wanted to think about broader forms of additive manufacturing. So not just printing, but knitting and growing and jamming and all sorts of other interesting ways that we can build up. So I'm really passionate about that. Academically, I run a program called the Design Minor, Design Major. And so that's obviously very related. And the minor was 2016, actually. So it's really interesting that that was like the exact same time I was here in sort of the same moment that both design programs were growing. And so we created this minor at MIT and allowed any undergraduate student to get a design degree. It eventually became a major, and then eventually that turned into the Morningside Academy for Design at MIT, which I'm part of. My lab is part of that, and then I run the academics side of that. So there's research and academics and fabrication and making and entrepreneurship and all sorts of other stuff. So I'm part of that. But mostly I'll talk about today the work of the lab. So I run a lab called the Self-Assembly Lab. It does not look like this anymore. It's way messier and crazier and it's a total chaos. But this is the space that we're in. And we have lots of researchers. This is probably outdated, but we have people from undergrad to master's, PhDs, full-time researchers. We have architects and designers, obviously, but we have computer scientists and brain cognitive and robotics and materials and mechanics. Really especially on the undergrad side, it's across the board. It's all across MIT. And I think that's what makes the work really special. So we work in 3 different categories or 3 different scales. So we think about materials, fabrication, and construction. But all of this is trying to figure out how do we build in a smarter way and how do we build smarter things. And one of the main ethos is how do we do that through materials and their relationship to the environment. So that's kind of the bigger picture. But if I step back a little bit, how did I get here? I studied architecture. I then went to MIT, studied design computation and computer science, and I was really interested in early computing. I was really interested in software. This is the first CAD tool. This is Sutherland Sketchpad, developed at MIT in the 60s, I think. That led to obviously lots of computational tools, whether that's simulation, generation, analysis, all the AI boom, et cetera. So computation fundamentally has changed how we design, but it's changed almost every discipline. The same thing holds true for fabrication. This is 1955, the first time they connected a computer to a milling machine. That obviously then led to all sorts of digital fabrication, laser cutters, water jets, printers, robots, all the boom in digital fabrication. And so just like code, fabrication also changed our field, our discipline, and many other disciplines. And so it became clear to me that code was a language for design and code was a language to make things. And then I started doing lots of digital fabrication work and installations and writing software to generate geometries and sending them to machines. This is a project we did at MIT for the 150th anniversary. But many others, you can imagine that kind of space. And maybe 10 years ago, there was this boom of the generative pavilion and lots of computational complexity. And I was drinking that Kool-Aid, like mass customization, and every part can be unique. But no one really wanted to talk about this part, like all the students, the late nights, the blood, sweat, and tears, the like brute force, and all the lack of elegance. Like there's so much elegance in the code, and there's elegance in the process of making it, and then like sort of just put that to the side and just brute force it. And that became really fascinating to me when I was at MIT in the earlier years, like thinking about why do we have code for design and code for fabrication, but no code for construction? Like how do we rethink the process of assembly so we can bring some of that elegance or all the capabilities embedded in the computational world? How can we bring that into the physical construction world? So that became my focus. And when I was a graduate student, I was working with Neil Gershenfeld's lab, the Center for Bits and Atoms, and it was under a DARPA grant, programmable matter. And that was like 17 years ago. And at that time, programmable matter meant programming robots. And so I was tasked with doing the large robots. Each unit was a little under a meter. And so these were large robots, and they would squirm around, and they would go from a line into a plane, or a line into a cube, or, different configurations. And at that time, everyone under that DARPA grant was all working on robots that would squirm and roll and reconfigure and disassemble and reassemble. But I started to become critical of this because, number one, it costs tons of money. This is right now the most expensive coffee table you could ever imagine. Like, I brought this home and it's just a dead piece of furniture that DARPA paid for, basically. But never worked again. It was super faulty. It took tons of people to assemble these things. It's really massive, lots of forces that it's fighting. Like, it just didn't seem to me that this is how we're going to build anything at large scales. So we need to think about, how do we embed all of the capability, the agency, the information, the transformation, all of that stuff, but how do we do it without the robotics part of it? Can we do it through materials? And so that became the focus of almost all of our work to this day, was just trying to figure out, how do we build more agency into our material systems, and to relate and transform and be active and adaptive with the environment around it. So there's three main categories of research that I'm going to walk through. The first one is on the material side. So this is what we call programmable materials. The idea that we take physical materials and we program them to change shape, change property, basically act as sensors, motors, actuators, have all the functionalities of the robotics, but embed them into the materials themselves. And part of that reason was the scalability question, like I was talking about before. We don't want to build every brick as a robot when we're building architecture. It's going to be too expensive, too costly, too failure prone, but we do want all the behavior. We do want all the capabilities. All of us are made out of materials. We're not made out of robots, and we have all of that information, complexity, capability built in. And so the question was, how could we do this at larger scales? In 2012, coming off of some of that work, I started then thinking about, how could we print these? And I just coincidentally ran into someone at a coffee shop that had a Stratasys shirt on, the printing company. And I was just like, well, why can't we print robots? Can't we find a way to print things that transform? And so that started this collaboration. It was just a total random idea at a coffee shop with a person standing next to me. And then they connected me with the material scientists, and they said, we have this weird material. We can't sell it because it swells a bunch, but maybe we can use that. And so that started the collaboration. And we print hydrogels in the joints. The hydrogels swell with moisture, and depending on how much of that hydrogel or the spacing of it, we can get different joint angles, basically. And so that was like the breakthrough that we had. And we printed all these structures, like a line that folds into a cube, or a line that folds into the letters MIT. These are all dipped underwater, and then they morph like a surface into an octahedron, or a flat sheet that goes into curved crease origami. And we did all these different shapes. Some were folding. In the beginning, we only knew how to do 90 degrees, and then we could do thinner mechanisms. We could do linear expanders. We even did this 50-foot long strand in the Olympic swimming pool. We did all sorts of structures that would go from 1D to 2D, or 2D to 3D. They would be folding, curling, stretching. And so this became like the early part, the demonstration that we could make these macro scale transformations without any motors, without any traditional electronics or sensors or any of the things that we think of as robots, but they still had the programming, they still had the agency. In this case, they're responding to moisture. We presented that, and then lots of people started coming to us and saying, this is great, but we don't care necessarily about printing, or we don't care about that polymer. Can we do it with something else? And even to this day, this question, like, how do we program every material with every manufacturing process? That's still about a third or a half of the work that we do is in that. Like, can we do it with carbon fiber and textiles and wood and metal and rubber and everything you can think of, and worked with lots of collaborators, industry partners, academics, much bigger list than this. But we did printed wood that morphs based on moisture, carbon fiber that is active based on temperature. We did these thin films. This is in the active matter book. They open and close with, this is an IR bulb, or you can put them in sunlight. We're doing a project with Google on an active shading system, basically stickers for buildings. You can put them on the windows and they open and close with sunlight. And we've done lots of different materials, but also different configurations. Like these are auxetic structures. They expand and contract uniformly. And then we started to put them on the body. So this one was like a sleeve. And basically we took these films and we slit them and then recombined them into this textile. And at that point, we applied for a grant through an organization called AFOA, Advanced Functional Fabrics of America. And that was right when Obama had created these manufacturing institutes. So there was a 3D printing one and a composites one, and then they created a textiles one. And so we applied to that and we said, you know, we've done it with 4D printing, we've done it with carbon fiber, we've done it with films. We think we can do it in textiles. Fund us and we'll figure out how to do it in textiles. And so we got that grant, and that led to now about a third or half of our work is just in textiles. So we've made active structures that sense pH, or in this case, it's active based on temperature. And these ones are really about tailoring. So the first application was, can you take a textile and morph it to fit the body? Can you create a perfect fit, like a customizable garment? Or if you know, like ski boots or shin guards or mouth guards or earplugs, these are products that you can morph to create a perfect fit. Could we do the same thing with textiles? And the two reasons to do that, one is to eliminate waste and SKUs. So if you're a clothing brand, you're going to have lots of inventory to get the perfect size or lots of styles. And the second is no one really likes to go to get their clothes tailored. So you don't want to like go get it hemmed. So could we create a perfect fit without having tons of inventory or having tailoring? So with Ministry of Supply, we did this project. We made 20 of these dresses. Every dress was identical, but then in the store, we have a robot that's heat activating it so you can get a perfect fit. So you can take the measurements of the person, but you can also change the styling. You can get like an A-line or a bodycon, or you can create pleats. So you can change the style or the sizing of the dress, but that way they can have one SKU, so one element in their inventory, and then they can morph it to create different sizes. So that's the first one. The second one is reversible transformation. So this is a custom fiber that we made. It has two different polymers and with different cross sections and colors. And these are all different combinations of experiments that we did to get that. The material property is important because that's how we get the reversible behavior at low temperatures. And then the knit structure is basically the architecture. It's the forces of the material to create different physical effects. Like how can we get it to fold or curl or bulk or create thickness or change stiffness? Like how do we get the material properties to change? And that has to do with the knit structure. So we change the architecture of that knit and you get different kinds of macro scale mechanical behaviors. And then you can change the zones. So like under the arms or the lower back or the chest, you can have different zones that have different behaviors. So we have material, the architecture of the knit, and then the zones. And by doing that, we can then create like these pores that open and close, like gills, or you can create flaps, or you can have thickness change. So this is another big category of work. With Arc'teryx, recently we did a jacket that changes insulation value. So think of like a puffer jacket that changes thickness. So there's a lot of applications in textiles and apparel where you would want clothes that become more breathable when you're hot, or become less porous when there's moisture in the environment, or change thickness to change insulation value. So we want our clothes basically to adapt to the surrounding environment, moisture, temperature, light, or the changes on our body. So that's like another big category. And then a third category started with this project around spacesuits. So we started collaborating with David Newman, who's the head of the Media Lab. She used to be a director at NASA, and her whole research is on spacesuits. And there's a specific type of spacesuit called a mechanical counterpressure suit. Normally the spacesuits, like the ones where they were just falling on the moon, those ones use air pressure to keep you safe in the vacuum of space. So basically put pressure on the body with air, but they're bulky, they're hard to put on. There's a lot of problems with that. If you puncture it, you can die. There's the other category, mechanical counterpressure suits, which is basically like wearing 20 pairs of yoga pants, like tons and tons of compression at the same time. And that also keeps you safe. If you pop it, you basically break a blood vessel, but you don't die. You can put it on easier. You can then move around easier. So there's a lot of advantages, but it's hard to make. So think about taking a sheet good. How do I guarantee that I have the right compression on my body with just a standard sheet of material? So what we did is we scan the body, then we create a custom knit program based on the scan. We can then ensure that we have exactly the right compression across the body, even though the shape of the arm, my arm versus someone else's arm would be different. But we can embed all these other things into it. So we can embed sensors in it so it can tell how the arm is moving or how much compression is. We can have different amounts of compression so that we did this like 2-stage compression, and that allows you to put it on and off easier. So you can have donning and doffing. On the outside, Svetlana from MIT studies different PE fibers. And so she has these PE fibers that are doped to do radiation shielding and debris shielding. Anyway, all of that work is really about embedding as many functions as possible into the knit structure. So normally, like, spacesuits are made out of 7 layers with all these different material properties. Or think about shoes, you have outsoles, insoles, midsoles, uppers. Can we embed all of those material properties? Super soft, super stiff, stretchy, rubbery, felt, thin, thick, all those mechanical properties we want to embed into the textile itself. Then to kind of expand on that, we did a project recently with Emico, the furniture company. And if you think about furniture, soft seating, they have all these different materials. They have PU foams, they have glues, they're all like cut, sewn, there's a lot of waste. They can't be disassembled and recycled. So what we were showing is that you could have all of the soft seating and upholstery for furniture, or think of car seats, or maybe even any other cushioning like shoes or other things. You can embed that into a single knit structure. So we make this what's called a spacer knit, but the unique part about this is it's a mono material. So it's a single nylon structure. So you don't have to have elastics. And most spacers have elastics, which means that they can't be recycled. We make this all out of nylon, but then when we heat it, it bulks. So it morphs and creates thickness, and that's what creates the cushion effect. And then you have tons of design freedom, but there's no assembly. You knit it, it comes off the machine, you put it in the oven, you get the cushion, and then you put it on the chair. There's no cutting, there's no sewing, there's no gluing, there's no foams, and then you can have tons of design freedom of where you put it, how thick it is, what kind of shapes, what colors, and it can connect right onto the stool. So we did this exhibition with them last October in California. So that's kind of a third category: multifunctional, multiple properties, minimize assembly, minimize components, minimize waste. But all of that textile work is just trying to utilize the knitting process much like a multi-material printer, like changing material properties, changing knit structures, changing material performance. But the benefit of knitting versus printing is that it's truly scalable. All of our clothes, our shoes, all the upholstery that we're used to is made in factories all over the world with the exact same machines. So it can be very, very scalable. If we develop something in the lab, it can go directly to market. Whereas with printing, there's a lot of advantages, but scalability is one of the downsides. You need that same printer in factories all over the world. So we're always kind of thinking about these trade-offs about design freedom, material properties, functionality, but also just scalability. So to get more into the fabrication and scalability part, as I was saying, one of the problems with printing is how do you scale these things? But there's also other problems. There's all sorts of printing processes, FDM, SLA, SLS, and new ones every day. And we started to feel limited by the printing processes that were available to us. And so we developed our own printing process a number of years ago called rapid liquid printing. And basically, we print inside of a tank of gel. The gel eliminates gravity. So we print in 3D without any support materials. The gel acts as the support. And there's 3 main advantages here. One is that you can print really, really fast. And the reason you can print fast is because you're not printing supports, and you also don't have to locally cure. With SLA, FDM, SLS, every single moment has to be cured because you can't move on until you're cured. In our case, it's curing because of a part A, part B chemical reaction. It's not curing because of the printing process itself. So we can just move on. We don't have to worry about it curing at that moment. So we can print fast. We can print large. We had a 5-foot by 10-foot machine. We can print small, and then we can print super soft, strange materials. Like typically with FDM, it has to be thermoplastics. With SLA, it has to be UV cured resins. We can print a wide variety of materials. Like we've printed even like concretes in there. We print foam, rubber, acrylics. You can do all sorts of interesting things, biomaterials, you name it. It's really wide open. So there's some advantages: speed, scale, material properties, but it also allows us to print inflatables. This is a project we did with BMW looking at a future car cushion The idea was that you could have this embedded in the section of the seat, and it could provide like massage features or lumbar support or even crash protection, a bunch of different functionalities embedded in this one cushion. But you could also morph it to morph around the body, or you could change the stiffness of it, for example. And so we can print that whole thing with all the inflatable chambers just by using that liquid process, which would be really difficult to do. We did a lot of other projects, like this is some home goods stuff like lamps and vases, but then we did footwear, we did prosthetics, medical devices, and then more recently we spun this out as a company. They're in Boston. They're launching the first machine in April. So that's like one path of research that goes through the lab. We develop a new process and then recently is spun out. But then we also question it, what are the limitations of that? And one of them was the temperature of the material, because if we went above the boiling temperature of water, then we couldn't print in that process. So we felt like that was one limitation. So then we started thinking about, well, what if we could print into powders? In this case, we're printing into glass beads, so very, very fine glass beads, and we're printing with molten aluminum. So it's almost the same as what I talked about before. We're printing in this powder. The powder supports the print. We can print fast. In this case, it's seconds. So we have a 2 foot by 4 foot bed, and we print under a minute in 2 foot by 4 foot. So we print very, very fast. The previous examples in the liquid printing, we were printing like tens of minutes, but it's also fully recyclable. So we can print the aluminum very fast, large scale, and then melt it down, print, melt, over and over and over again. We've done a number of different versions of this machine. It's still very much research. There's a lot of things to figure out. Zane Carson did his thesis on this, and then now is at ETH doing his PhD, but he developed the latest iteration of this, and he did these chairs. So each one of the components of the chair, like the whole structure of the chair, would be under a minute. So this chair would be like 2 minutes to make the metal structure. Obviously, the other parts are wood, or like 3 minutes to make this table. So we're really trading off speed for scale, speed for resolution. So we're going very, very fast, but as you can see, the resolution is fairly low. And one of the arguments that Zane has made is that you don't necessarily need the resolution at every point, because you can always post machine. You can always add the resolution that you need locally. And so we can go very fast and very large. You have solid aluminum cross sections, same mechanical properties as like a cast aluminum part. And then we can add threads or bore it to get the precision. Okay, another part of the materials work that we've focused on over the years is granular materials, and there's sort of two categories. The first one is looking at granular convection, and we did this project with Adidas, and I think Kim, who's here, worked on some of this work. And this project was really trying to think about how do we make footwear that starts off the same but evolves with all of us. So over time, my shoe becomes different than your shoe, depending on how I walk or run or the forces of my foot. So we use this principle called granular convection, where particles separate themselves. The more you try to mix them, the more they separate. And the dominant reason for that is size. There's some about friction, there's some about density, but size is really the main reason that they separate themselves. And so we did a lot of research on how do you control this and how do you guide certain things. In the end, we had 3 different particle types. One of them is this recycled rubber. So it's very dense, but it's fairly small particles. One of them is a medium size foam, and then one is a large size foam. And so what ends up happening is that we ran a marathon. Well, the robot basically hit the shoe in a marathon. A little bit easier than actually running a marathon. So the robot's going back and forth, running a marathon, and then you'll see the black particles at the heel toe show up. And those black particles are the really big foam soft ones. And so we showed that you can basically get the cushion to rise to the surface wherever you start impacting your midsole. So you can have super soft insoles that adapt to where you need it. And then the dense recycled rubber drops to the bottom towards the outsole. So basically we can guide the performance of the midsole only by walking or running, depending on what the shape of your foot is or the impact or how you use it. You can evolve that. So that's granular convection, particles sorting themselves. And then the other one that we focus on is granular jamming. So granular jamming is where particles get stuck. They act like a solid, but when they have freedom to move around, they act like a liquid. And you know this from the beach, if you just jump on the sand and it hurts and you jump and you feel like strong impact, that's because the particles jam. But when you play with the sand, they are soft and they flow through your fingers. In this case, you'll see it often with a bladder and particles. So we did this project with Google about like acoustic panels that you could continually jam and unjam and change the baffling of these panels. So you'll see those jamming grippers, and there's other kinds of jamming structures in the soft robotics community with particles in a bladder. And the backstory to this is we were at a conference in Chicago with a bunch of material scientists and physicists just focused on jamming. So the whole thing was about jamming. And at that time, I didn't even know what jamming was. Like when I got invited to go to a jamming conference, I thought they meant like jamming out, like music jamming. I was like, what kind of jamming are you talking about? And they invited a couple designers, and Gramazio Kohler from ETH and I were there, and a few others. And so Matthias Kohler and I were like, what can we do with jamming? We got to find a way to do something. Like, how is this useful for our world? So we got a grant together, and I flew over there for a month, and literally we were just jamming out on jamming. We went to the hardware store and bought a bunch of stuff, and we're like, how do we make this stuff jam? And the first thing that worked was chandelier chains and screws. That's what worked. Like, this is how this project started. It's kind of dumb thinking back, but we had no idea about jamming, and we were just like, let's try stuff. And so chandelier chain and screws worked. And then we were like, all right, well, what if we replace the screws with rocks? And that still worked. And then we were like, all right, what if we change this chandelier chain with string? And it still worked. And then that was the moment they're like, okay, we got something. We can work with this. And then they got a big Swiss federal grant and had 3 PhDs for 5 years working on this crazy stuff. And it became a big project, but that was literally the start of it. And so our main goal was use jamming in construction. And we had the rule that we couldn't have a membrane and we couldn't have a vacuum. Because if you have a membrane, it means your building can pop. And if you have a vacuum, it means you need to constantly be pulling that vacuum. So, it's energy intensive or susceptible. So we figured out this process where we could deposit rocks and string, and we exhibited this in Chicago at the Biennale. Place a big yellow bounding box, the robot's spitting out string layer by layer. The string is like a big printer. Each layer has different geometries. And when you remove the bounding box, the rocks fall away that didn't have the string, and only where there's string does it jam. So it jams because the string takes tension, the rocks take compression, so it equalizes the forces. There's nowhere for it to go. It acts like a solid load-bearing structure. It's really good at impact, and it's really good at dead load. It's not great at live load or vibration or abrasion, so that's definitely a weakness. But one thing that's interesting about it is that it's totally reversible. So at the end of it, you can wind it up, make a huge mess, and get a pile of rocks and a spool of string, and then you can jam it again, pile of rocks, spool of string, over and over and over again. And so that was the starting point, and my group then worked on this for a number of years. We did a bunch of different work. We're still actually working on it. We have government grants on this now, and my group focused on the construction side of things, like how do we make it as cheap and fast and low tech as possible? So using like coconut husks and rocks from Home Depot. Actually, the rocks in that project were Swiss rocks. We got them from this one company because we didn't know anything about it. We were so worried it wouldn't work. We brought rocks from Switzerland because we were so scared. We're like, I don't know, it only works with these Swiss rocks. But anyway, so now we work with anything like local materials, try to make it as fast and reversible as possible. And then the ETH side, they focused on the automation, like how do we make this fully automated with the robot depositing the rocks and the string and the slip form, etc. Okay, so I'll talk to you about one last category that we focus on, and that's self-assembly. So how do you take individual parts, bring them together to make ordered structures, even without human guidance, without robotic assembly, without any external layer by layer direction. Basically, we want these components to have the agency and the information to assemble themselves. And obviously that is built off of all of us, our natural world. But I also think about like planetary scales or geological scales. So it's because many people who know self-assembly, so either most people will say, oh, you mean IKEA, and I don't mean IKEA. Like that's not the self-assembly, like I'm not the self. Or they'll talk about biology, chemistry, material science, like very, very small scales. But if you skip over the human scale, you go to the large scale, the same thing happens, like planets form themselves or mountain ranges, geological processes use self-assembly or self-organization. And so we're interested in both of those ends of the spectrum, but most of our work is on the larger scale. And this started with a project with a molecular biologist, Arthur Olson, and he's at Scripps, and we made these biomolecular models. So this one is a poliovirus model. And so you shake it hard and it breaks, and you shake it a little bit softer and it comes back together. And there's 3 reasons that this works. The first is the geometry of the component. So if you have, in this case, pentamer structures, you get this dodecahedron. But if you have a different geometry, you'll get different kinds of things. The second one is the connections. In this case, it's magnets, but you can use surface tension, you can use Velcro, you can use all sorts of other kind of stickiness. And it's not actually the pulling force of the magnets, it's just the stickiness. But if anyone's ever played with buckyballs, just having a bunch of magnets doesn't lead to anything useful. So it's really about the patterned connection. So it can't just be like a bunch of magnets randomly. It has to be like positive, negative, positive, or negative, positive, negative, or positive, positive, negative, negative, like all these different patterns. And those lead to error correction. And so you need to basically guide successful structures and weed out incorrect structures. And then the third thing is energy. So too much energy, everything breaks. Too little energy, nothing happens. But there's thresholds in between. You need just the right amount of energy for assembly and a different kind of energy for disassembly, or a different amount of energy. So these are the basic ingredients of why this works. And we've done lots of experiments. This one is components underwater. Each part is unique. They have lock and key mechanisms with positive and negative interactions, the magnet and the geometry to make the chair. Or this one is Velcro nodes. So weather balloons filled with Velcro nodes. In this case, they make lattice structures. So we did it over the course of a weekend, and we filmed all sorts of different kinds of structures that assembled. So these make these lattices, and they can just keep growing. If we had more units, then they would keep growing in different ways. Everything sticks to everything, but here everything's Velcro, which is interesting. And we wanted to prove that it's not magnets, because oftentimes when anyone hears it's magnets, like, oh, I get it, it's magnets. But I'm like, all right, play around with magnets. Tell me if you ever make anything interesting. Magnets, are cool, but they often make a big mess. And we wanted to show that actually it's just pattern stickiness. So even though we're using Velcro, the way that we got the error correction is that we had a node that basically has half positive and half negative Velcro, so male and female Velcro. And if you connect on the wrong one, you won't attach. If you connect, but you're more than 50% off, you're going to be pretty weak. So over time, you're going to break off. And so the closer you are to being connected on, you're going to be stronger. So there's, benefit to being more accurate there. And then when 2 connect, they can still rotate. When 3 connect, they can still rotate. But when 4 connects, it creates a plane. And so those mechanisms allow us to have some kind of geometric error correction so that they still ensure precise structures assemble. So anyway, we did a lot of experiments over the years, small things, small meaning like several centimeters, not nano small, all the way up to like meter scale and different environments, water and shakers, et cetera. But all of this work felt very abstract and very academic. And then it became very, very applied. So we got invited to the Maldives, and we've been working there since 2015. And the project, I was always thinking about self-assembly as this fascinating thing, but I didn't know why it was useful. People would be like, oh, how is this going to influence architecture and construction? And, it always felt a little forced. Like, how are we going to use this? I don't know. You can dream up some building that self-assembles, but it's a little bit like, doesn't feel like the perfect fit. But when you skip over the architectural scale and you look at the geological scale, it's like, okay, now it makes sense again. Because all of these geological processes also are formed through self-organization. So when we went to the Maldives, it became very clear that that was the project. Originally, they invited us to do an underwater installation. And then when we got there and we went to some of these islands, it was like, no. The project is about how islands self-form. We need to think about utilizing this process of self-organization. And the real problem that they were addressing was sea level rise, coastal erosion, increased effects of climate change. And there's really only 2 things they do. They either build walls, breakwaters, groins, barriers. And in that case, it almost never works. Nature always wins. Eventually, it's going to break down the wall, or it amplifies the negative effect and it creates more erosion than initially. And the other one is dredging. So they'll just pump sand from the ocean, pump it back onto the beach, and rebuild your beach. This happens in every coastal community around the world, most likely. It's super expensive, it's super damaging, destroys the coral reefs, etc. So it's not great. In the Maldives, they do this. They can create an artificial island in a month. So all the islands north of that, they're all artificial. And we became interested in the same amount of time that island formed. These 3 sandbars formed themselves. So these sandbars come out of nowhere. They're over 1 meter above sea level, sometimes even more. They're many meters in any direction. So they're very large. This is one of them. This is the first thing they took us to, was this sandbar. And they said it showed up last month. Like out of nowhere, this sandbar comes, and it's massive amounts of sand. This would be many millions of dollars to dredge this. And it shows up out of nowhere. It comes every single year. And so that became the project. It was like, why does this happen? How does it happen? Could we understand why these islands are forming? And if you could you promote it to happen? So we've been studying that. By no means do we have the answer to this. It's people spend their whole lives studying this, and it's not a solved thing by any means. But our main hypothesis is that it's a relationship between the force of the ocean and the bathymetry. And if you change that bathymetry, you could potentially change how sediment accumulates. So that's our working theory. We're not going to be changing the force of the ocean. So there's currents, waves, tides, storms, tsunamis. We're not changing that part, but we potentially could change the bathymetry. And so by changing that bathymetry, then you could guide accumulation. So we do a bunch of different things in the lab. We study this from like a coastal side. So you can look at coastal geomorphology, how coastlines change. Then we study it from like a physics simulation standpoint. So we study how the flow of water and sediment interacts with that bathymetry change. So the white objects are objects that we place underwater. And then we study how would the sediment accumulate based on those objects in the flow. And then we do lab experiments. So we have flumes, and we set up, in this case, a wave tank. And then we have ones that flow current, and then we can change the tide. So we set up these tanks. In this case, it's a bladder. It's this like ramp-shaped bladder. We place it there, we pump waves, and then we study how the sand on the right-hand side accumulates based on the shape of that object on the left-hand side. And then we have another tank where we have 8 pumps, and we turn on and off these pumps, and then they self-organize the sand in the middle just by changing the flow of the water. So imagine this is like a satellite view, and you're looking down, and there's different monsoon seasons, and you're seeing how the sand is self-organizing. So any one of those could be a sandbar, or it could be, accumulations of sand. And so we started studying this to understand how the sand self-organizes into these patterns. And then we started doing computer vision and machine learning on it, and that then led to some satellite work I'll show you in a second. But most of the work is field experiments. So we have the unfortunate luck of going to the Maldives, as you can imagine, is a kind of amazing place, and we try to go there twice a year. So we go there in the fall and in the spring, right when there's monsoon season changes. So there's 2 monsoons, and they switch 180 degrees from one another. We've now done 10 of these, so it's a little outdated. And these are, several meters. So the smallest one would be like 20 meters, and then the largest one we've done now is 90 meters. So these are big structures. We place them underwater, and they're totally passive. So we just place them, and we leave, and we then monitor them through bathymetry surveys, drone surveys, and satellite images. So this is one of the first ones we did, 20 meters long by 4 meters by 2 meters tall. So it's 2 meters in height. Initially, we started to see about 0.5 meter of sand accumulation in a couple of months. And then more recently, the sand now is all the way to the top. So we've gotten 2 meters of sand in net Z height accumulation in just a few years of placing this. So just placing it, doing nothing, going away, we got 2 meters of new Z height. And we have about 0.5 meter to go before we reach the surface of the water. And then it's 20 meters wide by something like 80, 90 meters in the zone of the accumulation. So this was a first nice success for us. More recently, this is 90 meters across. So those little things, those are people swimming. And actually the funny thing is that that's the ambassador, the U.S. ambassador to the Maldives, and USAID, although now this was USAID funded, is now all killed. unfortunately, but these are like the diplomats going there swimming, which was pretty funny. Anyway, so we made this 90-meter structure, and the idea here is that it would be omnidirectional. So think of one of those as the previous one I showed. It was quite successful, but it only worked half the year. So now we want it to work in any orientation, any storm direction, any monsoon season. And so now this is after, I think we installed it last summer. So maybe we're 8-9 months, something like that. So you can see the large amounts of sand accumulating. So here you can see some aerial images of that, of the sand accumulating. And then this is what it looks like underwater. So now we have only 6 inches left before we breach the surface of the water. So that drop there is about 2 meters. And that thing all the way in the back, that dark thing, that's a person. So you can kind of get the scale. These are large amounts of sand accumulation. But we've done other ones. We did quickly deployable ones. These ones, you can make 40 meters in about an hour. And these are more like gardening. So you could have lightweight modular units that you deploy for one season. You move them to another part of the island and shift them around, sort of like gardening with sand. But more literal gardening, we also are interested in how vegetation accumulates or traps sand. So then on top of the early one, we basically created these floating gardens. So we made this floating structure, and each one of them we had local vegetation like screw pine or mangroves, and they would float over the structure. And the idea was that as the sand is accumulating up in one season, the vegetation would grow down and they would start to stabilize and trap more sand. So we float these little garden units in there, and eventually they look like this. And so that's another approach that we've been looking at. And so everything on the structure starts growing, but then the vegetation also starts to grow from the top. And then this is the most recent one. So we made 54 of these units, and we deployed them off of a beach. This is the first time that we did a beach location. The previous ones were in a lagoon flat, which is more like the dredging problem. The beach location is more like an erosion problem. Like, how do you stop erosion on the forefront of the beach? Each one of these units is cast directly in the sand on the beach, and then they have this amphibious excavator, and they drive out there and they place them. Every one is unique, although they're cast the same way. So they are cast directly in the sand. They pull them out of the sand, drive them out, and place them underwater. And so this is what they look like. They're a little over a meter in any dimension. We made 54 of them. And then in about a month later, this is what it looked like. So they're like 3/4 of the way filled with sand. So, you have, I don't know, 3/4 up, maybe some are a little more, some are a little bit less, but like lots of sand in a very short period of time. And then the idea for this was the first time that we would bring together the sand accumulation research we were doing with the marine life. So we've been doing a lot of work on like, how do you take local material made out of sand, you fire it, you can turn it into lime, you add water and sand back in, you get concrete, and then you can grow coral on it because it's all calcium carbonate based, and they have different geometries and textures. So we're hopefully over the course of the next several months, years, we'll start to see a lot of marine life growing. So that would be like how to create a positive benefit for the marine life, positive benefit for the beach and the sand. And then also it becomes like a dive site. So hopefully create this habitat for fish and other local species. And then the last thing I'll show you on this is we started doing a lot of satellite work. So we track these islands and sandbars, and then we can monitor how they're moving, how they're changing. You can see some of them move a ton, some of them hardly move at all. And then what we're building now is a platform to try to predict that. And so we basically analyze all the satellite image and then try to use that through machine learning to predict how the islands will change. And that is the work in the Maldives. All of that is trying to figure out how do we build and collaborate with the forces in the environment. So instead of me shaking things or putting them on pumps underwater, can we just use the natural force of the ocean, waves, currents, tides in this case, and accumulate, basically collaboratively build with natural forces. And then more recently, we've done one in Iceland with lava flows. And so we're waiting for the next eruption. We just placed these structures out in front of a volcano. So there's a lot of crazy forces in the environment. And I think any of them are rich for this. Okay, so where's all this crazy stuff going? I said in the very beginning, our research interests are how do we design in a better way? How do we build in a better way? How do we make smarter things? And this is the main paradigm today. Like, you want to build a smarter car, a smarter home, a smarter shoe, a smarter shirt. put more stuff in it, put more batteries, put more motors, put more mechanisms, put more electronics. And that's the main paradigm for smart. And the main problem there is that adds more cost, more failure, more components, more assembly time. So none of that is smart. So then you get in this problem where the smart thing is dumb and the dumb thing is smart. So how do we get away from that cycle? And if you go all the way back to the DARPA programmable matter grant, all of the researchers, more than a decade or a decade and a half ago that were working on that, most of them have shifted away from electromechanical robotic systems into soft system, whether that's granular jamming, whether that's biological materials, whether that's multi-material printing, whether that's, all sorts of different softer material-based robotic systems. And so I really think there's a shift from the electromechanical into smarter and smarter materials. And really there's a collaboration here because robots are great at not getting tired. They're great at precision. They're great at programmability. But materials are great at physics. Materials respond and transform and adapt to the physical world. They don't have to be programmed to do that. They already do that. And we can just tap into it and amplify it. And humans are great at creativity and collaboration. So we really need to work together. And so I think the future of robots is actually towards smarter materials, less towards electromechanical systems. So the vision of the lab is today we build smart robots and machines, and tomorrow we'll build smarter materials and environments. Thanks so much.
Well, thank you so much for your talk. This was very exciting. I noticed throughout the presentation, you had a lot of focus on these exciting things that just came out of chance through experimentation. But I'm curious as to what maybe were exciting failures that you had that allowed you to iterate through more ideas that way.
Yeah, great question. And maybe first, before I tell you about the failures, there's a million failures, and we can talk about some dramatic ones and hilarious ones. But I will say that I think that is one thing that's unique to people in the design world, whether that, that have some architecture background or even artistic practice, some creative discipline. I think it's unique to really embrace experimentation and play and creativity and dreaming and failure and being okay with abstraction and the messiness that's involved in the creative process, I think has been very productive for our work. Like just the jamming projects being like, I don't know about jamming. I don't know anything about this. We should figure it out. I'm probably not smart enough to understand this from a technical standpoint, but I can play with this stuff and figure out what jams. And then once I see something jams, like, okay, we have something. Let's figure out why that works. Let's study it seriously for a long period of time. But like in the beginning, it's just playing around and just trying to discover something with a hunch. Like, I think this is going to work. Let's figure out how it works. And almost everything we do in the lab is physical. I mean, yes, we do lots of simulation and yes, we do lots of computing stuff, but like, that's definitely not our work. We don't ever write papers on that. That's not our main contribution to the world. Like, that's not our strong suit. We do it somewhat, but like everything we do is physical, and almost everything we do is just like lots and lots of failures and experiments and playing and weird ideas and just like trying stuff. And then you get some weird surprising moment and something happens and you're like, oh, okay, that's it. Figure this out. Why does this work? How do we tap into that? How do we amplify it? Like, focus on that thing. So I don't know how to articulate that better, but like playful experimentation, I think is really critical. We've had crazy failures. I mean, many of the Maldives things haven't been super successful. A few of them have been very successful, and lots of them have just like not done anything. Or the worst case, one of them we put out and the next day it was gone. Like, spent lots of money and lots of time, is just where it's gone. It's like not there anymore. Like, where did it go? And some of them, yeah, in a month it disintegrated. I didn't show some of them, but like some just disintegrate, some get destroyed by the next storms. Some people steal it. There's also sand pirates. I didn't say about that, but there's people that go there and they literally steal sand and they sell it. And so they go to our site and now they just steal our sand. And we're like, no, we're trying to show that sand accumulates. And you're like out there scooping up our sand. So there's a lot of weird things like that. We built a 65-foot tower on campus for this big celebration and it collapsed. So that was a huge failure. That wasn't good. Yeah, there's a lot of failures that we've had over the years. I have a really complicated relationship with failure because I'm not afraid of failure and I embrace it. And I think that's part of it. And it's super critical for research and play and discovery. Um, but most of the world doesn't want to know about your failures. They say they do, and we all talk about like testing to failure. I mean, Meejin like created a book in our department when she was in our department called Testing to Failure, and we all talk about that and we love it as like an idea. But like, you're not going to show up to MoMA with a failure. You know what I mean? Like, no, you can't like have a public tower for the celebration that fails. Like, no one wants to hear that. So it's a really complicated thing that I'm always struggling with. Like, when do people say they like failure? And then when is it not okay to fail? And you just need to understand that. And we're always riding that line because there's like big money on some of these projects, you know, whether, especially if they're industry projects or they're like, whatever, there's someone that wants something delivered at some time, you know, and most of them are not as generous as NSF or something where they're like, yeah, go discover and just write a report and tell us what happened. You know, like most of these, like they really want something to be delivered. So we're always on that edge of like, is this going to work or is this going to be like really bad? And luckily many of the things have worked out. And also I think part of it is the relationship with these folks and like bringing them along in the journey. And so they understand that this is research and they understand that not everything's guaranteed. And like, even if we have failure, we can still learn from it and we can do better the next time. And luckily in the Maldives, we have amazing partners. And so, yeah, it's okay. If we fail, we just adapt and try better the next time and keep going. But yeah, it definitely can keep you up at night if you have a big deadline with a big client with a lot of money on the line and your reputation and like the thing fails. It's not good anymore. But it's totally fine to fail in the lab every day. And I don't know. I wish it was more clear, but yeah, it's complicated. It's a love-hate relationship. Yeah. It's all fun.
So I have a complicated relationship with smart materials.
Me too.
I'll tell you what I mean. Like in my world of origami, people will do things like they'll show that you can create and or gates, computer programming with origami or with microfluidic devices. But it's really hard to beat, you know, CMOS, right? Like electronics. You're never going to beat, you know, the scalability of CMOS electronics is unparalleled. You're never going to beat computer chips with sort of computing. So, but I understand smart materials and I understand sort of embedding intelligence, but it's always sort of this very weird, like when are you doing it in a good way? When are you doing it in a dumb way?
Yeah.
And I'm sort of wondering what your, you know, ideas are.
Yeah. And I will say that I'm definitely taking like a provocative stance here. And I don't think that it needs to be that extreme. You know, there's definitely lots of hybrids. Even the spacesuit, like it had electronics embedded in it. But not everything was electronics and some were materials and some. So I think there's lots of hybrids and most likely that's going to be the future is that you have hybrids of different kinds of smartness or intelligence. But I think just conceptually, I'm really passionate about the material side, but it's not great for everything. Like global communication is way better to do with electronics than it is to do with materials. Like it's really hard for a material here to talk to a material over there or to talk to the material on the other side of the world. And that's like fairly easy to do with electronics. So there's certain things, but like let's say you want to make some little actuator that responds to temperature and does this thing or whatever, like you're doing a lot of hard work to get this thing to move based on temperature when I could choose a different material and it's automatically going to do that anyway because it's feeling the environment around it. So there are certain cases where I think, and a lot of the apparel examples fit into that category. They're, you know, trying to do a lot of things that respond to the body or the environment using electronics. And so I feel like most of that is just that we collectively forget about this. Like before we had electronics, we had to think about material properties, think about like shipbuilding or alcohol barrels that swell, or Japanese joinery, or like the marine chronometer. Like a lot of these things were based on material properties that expanded and contracted, and you got some kind of smarter behavior or performance. Then eventually we get like more traditional smart things with electronics and sensors and actuators. And so then we start to forget like the material properties matter. It's more like, oh, if we just put a bunch of motors, then we can make it do anything. And so you start to like lose the inherent understanding of how materials can respond to their environment, but they can't do everything. So I think the question is like, when does it make sense for it to be material based? When does it make sense for it to be some other actuation? We use a lot of pneumatic systems, you know, and is pneumatics better than electromechanical? I don't know, probably not. I mean, it's, you know, yeah, for our lab, and part of this also is just that like, we aren't that great at electronics. Like that's not our specialty. So we tend to just not do electronics based projects. Although sure, we use like CNC machines and we use computers all the time. And, you know, we do use electronics, but we don't typically do like, smart wearables with sensors or actuators embedded in them, you know, or like electronic robots or whatever. We try to focus on the materials, and that part of that is just like, how do you specialize? But I think each one has different advantages. And I'm teaching this space architecture class, and we've been doing a lot of space stuff recently. And I think in those extreme environments, that's where it's really clear why some have pros and some have cons. Like in the everyday world, yeah, it's not that hard to just like plug something into the wall. But when you're in space, like you have super extreme constraints, and some of those like air pressure is really great or really bad, or like using battery power is like gonna kill the whole crew. So you really can't like use any more batteries. So we really need a completely active but passive system. So you have these different trade-offs. Like we're doing this rover project right now, and if we really can't use any, there can't be any power draw. So it has to be completely passive, but they need active thermal control. So I think those are good ones where you're like, okay, it rules out. Or we did a project with Airbus and they didn't want any additional weight, no extra components, no extra assembly steps. So that's why they were ruling out electromechanical, hydraulic, pneumatic actuation. So I was like, we needed to be a single piece of carbon fiber that actuates. So I think those extreme conditions are where it's like, okay, this is where materials make sense. And this is where electromechanical or pneumatic or something else would make sense. But you know, they all have positives and negatives, and we do think about those. You could do a hybrid where you have, a lot of times people point to control as the reason. Like, well, in electronics, I can control if the flaps on my shirt open and close. And in the passive one, presumably it needs to just recognize the temperature change outside. But you know, what happens if it's like your body is really hot, but it's also hot outside or something? You know, like there's different conditions where maybe the passive one doesn't always work. And so you could have it that it electromechanically actuate, or electroactive actuates the material. So you could have some control systems like a hybrid system. But I think it is just like a constant debate, or constantly thinking about when does one system make sense or the other.
We have a couple questions online, Skylar, from Yiwen Yang, who asks, regarding the cost of 3D printing, how do sand printing and gel printing compare in terms of efficiency, material waste, and scalability? Are there any strategies to optimize their cost effectiveness for large-scale applications? And the second question, related, in your large-scale self-assembly research, what potential applications do you envision at the urban design scale? How could self-assembling structures contribute to adaptive or sustainable city planning?
Yeah. So the first one, in the printing processes, so both of them are very low cost. And there's a few reasons for that. One is that we don't use super specialized materials. So we're just using like literally like waste aluminum stock from the water jets around campus. So we're just using like standard stock aluminum to print with. It's not like some super specialized powder that needs to be sintered. It has to have all these very specific properties, which is where the cost of printing usually goes up. The other cost is the machine. That's a little more complicated to understand because the machines in our lab are fairly cheap because we're making them and they're, hacked together with various things. Then the machines from the commercial side, I'll let you talk to them when they launch the machines. And so I think that's a different question, but that most of that has to do with what industry is it focused on, and what price point does it make sense from a business standpoint. And are you doing like at-home printers? Are you doing industrial manufacturing scale printing? So I think the cost of that doesn't really have to do with the cost of what you're talking about there. So the materials are cheap. It's much faster, so that makes it cheaper as well. And then especially the metal part, it's totally recyclable. You can just keep melting that back down the print that you made. So I think there's a lot of signs pointing towards these processes could be much, much cheaper than traditional printing. And then the second question on urban implications. Yeah, I think that there's a few different ways you could look at that. One would be things like climate, the facade project I was talking about with Google, where you basically can put stickers on buildings or change facades of like large parts of the city. So I think you could look at it from that, like what are components, material components that we design that you could then have interfaces or interventions into architecture that could adapt to the environment or change. We did a project that was about like morphable meeting spaces, so interiors, exteriors, maybe structure, whatever. But from like an actual urban point of view, I think it probably goes closest to the Maldives work, where think about in New York, what is Bjarke's project called? It's not the High Line, the other one. What is it? Court Scraper? Yeah, the one that's on the edge of the water. They did this like, is that what it's called? Court Scraper? Okay. But there's like, there's coastal barrier project to like stop Manhattan from flooding. And, I think that many coastal cities have this problem of how do we interface with a complex dynamic system like the ocean. But every day we walk outside and we have to deal with the complex dynamic system of the weather. And we do that by changing our clothing or changing with umbrellas or staying inside or outside. Like we adapt as humans. The problem with our urban environment is that buildings don't do that. They can't just get up and move. They can't just put a new jacket on or put an umbrella on. So like in the Maldives, for example, everyone's like, oh, the Maldives are going underwater. They're screwed. First of all, there's a researcher, Paul Kent, showed the Maldives are actually getting bigger, outpacing sea level rise, which is really interesting. And there's a lot of questions on why that's happening. But anyway, so that's the whole thing. But I started to think about, actually, the Maldives will probably outlive all of us and outlive all the cities we know. Like these islands aren't going anywhere because the islands are growing, changing, adapting, moving, morphing. They're literally organisms. They're literally alive, the islands. But the buildings on them are screwed. And the capital city of the capital city of the Maldives, Male, is literally like Manhattan. I think it's the most densely populated city in the world. And it's just like concrete jungle straight to the edge of the reef. Like they basically deleted the island. They built concrete walls all the way up to the edge, and it floods all the time. It's totally going underwater. And that has to do with how we built the city, because the city can't adapt. It can't adjust. It can't do anything. It can't grow, change, move, flex. And there's no live edge. There's no changing, morphing, dynamic interface between the ocean and the natural system and the built environment. And so I think we need to focus on those interfaces and have much smarter, adaptive, dynamic interfaces. Best case scenario, we find a way to build cities that can adapt, change, pick up, move, grow. I don't know how to do that yet, but that would be the better scenario. And they could grow the same way that the islands are growing. But until that time, we at least need these dynamic interfaces.
Thank you so much for the talk. I had a question about, I think I've been thinking a lot about recently how these more experimental material practices, like I feel like I often see super amazing things happen in academia, but then how do you get people outside academia convinced about it? And I think I found a lot of inspiration in your work. Just the fact that you're working in some cases in like footwear, product design, a smaller scale to the larger scale. So how have you used these scales, or could you speak on that a bit, how you've used these scales to maybe connect with people in a different way or when someone can hold something, does that change their perception and maybe buy into looking at these problems on a larger scale?
Yeah.
Thank you.
So I think one thing you'll notice if you look at the early work to today, it went from like very abstract, almost trinkets doing weird things into like very applied. And part of that is just a natural evolution of the work and of our interests. There's a lot. So I have a lot of thoughts on this. I think about this a lot. Like, academia is really great for intellectual freedom. You can explore the things you want to explore. You can go as deep and nerdy and as weird and wild as you want to go, as long as you make a contribution to the field, as long as you make impact and you do something great. But it doesn't have to be useful. It doesn't have to make a profit. It doesn't have to truly have impact. It has to be new knowledge, but otherwise, you don't have to care about the rest of the world. But to me, that gets kind of boring quickly, because it's kind of a fairy tale world. It's like we live in the world of ideas in academia. And how many cool ideas that don't matter are you going to make? You know what I mean? We've just made lots of ideas that are cool that don't matter. And eventually you're just like, what are we doing? Like, how many more cool trinkets are we going to make? So you start to think about those things. And then one thing academia is really bad at is having impact in the world, other than through ideas. So ideas in academia lead to changing the world, for sure. New publications, books, new directions, new fields, whatever, sure, certainly. But direct impact from the work that you do, how does it get to the world? It's hard to do in academia. It's much easier to do in a startup or in a large company, or in government organizations or other things, because you are in the world. You interface with people and systems and species and whatever else. It's harder to do that in academia. And so I've just over time really tried to figure out, how do we do that? One way to do that is to spin out companies. That's certainly like an entrepreneurial version of it, or like for-profit or nonprofit. You go in that direction, and there's positives and negatives. Like, you have to be super laser focused, but you can have a lot of impact, and you can reach a lot of people, and you can try to do something that you're interested in getting out into the world. Another way is to partner with organizations and to do work in the world, like the Maldives Project. And that's not really like an enterprise, but that we take our research and we actually just go and do it in the field. So you can definitely go that direction. There's a whole nother angle here, which is just funding in general. So if we talk about that, when I started the lab, there was a government shutdown. We've had several of those since then, but it was a government shutdown. And I remember talking to some of my senior colleagues, and they were like, don't go after government funding. And, you're starting a lab, you have no money. You're like, okay, well, how do I raise money? At that time, I also got the TED Fellowship. And then I, got put on the stage to talk about these things. And I realized, like, this doesn't resonate with anyone. Like, this weird thing that moves, like, who cares? Like, no one cares about this. Why does this matter, other than like me and my nerdy friends? So I think that was a moment where I started to think about, like, how do I articulate this so that anyone else in the world knows what I'm talking about and it matters? Like, why does this matter to anyone on the street? Like, who cares? So you start to think about your work in a different context, and you start to try to articulate it in a different way or reach a different audience. So I think that was really inspiring and helped me to kind of shape the way that I talk about the work, or the way that I document the work, or like, how I reach. But it also led me towards an industry focus. And so that became the way to fund the lab, was like, okay, we'll collaborate with companies. If government's shutting down, I can't rely on that. So we'll do industry funding. And, academics have different perspectives on this. Some people really don't like industry funding. Some people really do, so, whatever. But I found it to be really great, because maybe as architects, we're used to this. Like, yes, we have deliverables. Yes, we have to deliver things on time. That's how the world works. And I think academics aren't used to that, because NSF and other ones, which I love, by the way, are really, like, over time have gotten more and more of this, are wonderful. Like, that you have total freedom and you don't have to deliver much. But that's just not reality in most of the world. And so I'm just comfortable operating in the other spectrum of, like, you give us funding around a specific topic problem. We'll create something interesting together, and we truly collaborate. Like every 2 weeks, we work with those partners. We meet and we like literally work together for years on end on projects. I think they're much better for it because we work on very real problems that are important to industry that we learn about. You know, many of the industries, we don't know anything about it. We've worked on orthodontics to like medical devices, to shoes, to cars, to like, we don't know anything about that field. And then you learn a ton and you learn about these important problems in that field. And then you work on something hopefully that's new and creative and useful. And then when it comes out, it has like relevance to people. They understand what you're talking about. This weird thing like granular convection, if I did it in a little jar, I'd be like, okay, who cares? But then you put it in a shoe and people are like, oh, I get it. That would be, oh, I want shoes like that. I want my shoes to adapt. Now people care about granular convection. I mean, probably not, but you know, they care about shoes that adapt. So anyway, I became like really interested, and that became 75% of our work is funded through industry probably. And then, you know, government grants are the rest and some other stuff. But you know, so I think it comes from all angles. It's like some is funding, some is like, how do you build relevance? Some of it is, what do you want to do? Do you want to write papers? Do you want to write books? Do you want to start companies? What do you want to do? And so academia is good for certain things, and then you have to find ways to get out of academia, I think.
Skylar, thank you so much. I have one final question. To a audience full of students engaged in learning across disciplines, researching and designing across disciplines, what are 3 pieces of advice that you would give them?
Oh, that's hard. 3. I probably have too many, but I think one is the play. Like, just have fun and play and experiment and be creative and be silly and be weird and have fun. Like, I think we often tend to just do the thing that seems like we should do. Like our parents tell us what we should do, or our society, or like our discipline. You know, this is the thing. Like, I got to work on AI because I'm gonna get my job, or got to do this thing that like my parents say I should do, or the really important thesis would be this. And sometimes that's important, but I also think just like, what do you personally just want to play with? What do you want to like, what's going to keep you excited? So I think play has been really important in the lab and just throughout our career. But as I was saying before, I think it can't be that only, because you can then get caught in this like artist cycle of just only talking to yourself and only doing weird things that no one cares about, and you're just like playing and playing and playing. So I think the second is like, how do you resonate with other people? Why would anyone care about this? How do you connect to some other group? And don't go to the same conferences with the same people. Like we love Acadia and like go to Acadia every year, but like you can't only go to Acadia because that's all of us just talking to us. Like, you know what I mean? Like, we got to go to these other ones, you know? And so you do a little bit of the Acadias and whatever your conference in your field is. And then you go to like go to like the dentistry conference. I don't know, whatever, like go to some other thing that has a bunch of people doing other stuff that you don't know, or go to a jamming conference like that you don't know anything about, and just like, yeah, explore some other world and try to find a connection to some other discipline, some other community, some other group, like find relevance in the work. Yeah, and I think maybe the third one connecting to that is just that in order to be cross-disciplinary, it's a really fine line between being ignorant and doing anything interesting. You know what I mean? Like, because a lot of times we enter these fields and like, I don't know anything about sediment transport and geomorphology. And there's people that spent their whole careers on this. So the tendency is like, you walk in there and be like, yeah, I can do this. And especially from the design community, we get like, we have this like ego where like, I can figure it out. I don't know, how hard can it be? We can figure this out. But I think people can get really pissed off by that. They're like, I'm an expert in this thing, you know, like I've spent my whole career. You don't know anything about this. So that's a really fine line. And I think that really has to do with collaboration and like just people to people collaboration and like personalities and relationships, and like trying to understand and finding when is the moment to, I mean, it's always fine to just be like, I understand that and you're an expert, but like, I trust you, but could we do this maybe? Like, and just try to push in different directions, not trying to be the expert. It's a complicated field, but I think, or a complicated space to be in, to always be uncomfortable in a discipline that you don't know anything about. And there's a whole field of people that are experts. But in that, how do you find a way to still operate and do productive things that hopefully that discipline looks back and says like, wow, you really contributed something. Like, I wouldn't have bet on that. I thought you were going to completely fall on your face, but wow, you actually did something here. You might not know why you did it, but you did something that's interesting. You know, like, I think that's the best that we could do, because we can't be experts in any of these things. Or wait, we could be experts in one of them, but we're not going to be experts in all of these things, right? And if you choose this kind of cross-disciplinary, creative, interdisciplinary world, you're kind of choosing the generalist direction, for better or worse. But how can you not just stop at being a pure generalist? Like, how can you collaborate with experts, and how can you make a contribution in other fields if you don't know that much about it? And that, like, I don't know exactly how to do it, but I think that's a really delicate space that we all need to tread in if we want to be in that space. And I think most of it just has to do with collaboration and finding a way to talk about it and try to learn and be humble and collaborate with the right people. Yeah.
Great. Thank you so much, Skylar. Everyone, please join me in a round of applause for an excellent lecture.